Hello and welcome again. We have been discussing the theory of superconductivity, microscopic theory. This was as I said formulated first by John Bardeen, Leon Cooper and Robert Schrieffer at Urbana-Champaign in the US. They proposed a complete microscopic theory of superconductivity in a long paper in Physical Review, and that paper is a seminal paper that is an example of how a thorough calculation and detailed work needs to be done and of that high quality. So, that paper of course won the Nobel Prize in 1972. The whole idea of superconductivity, as I mentioned, was hinged was the fact that there is an attractive interaction between electrons. They must form a Cooper pair, a pair which later on came to be known as Cooper pair, and that pair condenses to become a superconductor. So, that is the line of thought that finally culminated in formulating the theory of superconductivity. In this context, I must mention that in the USSR, Landau and Ginzburg were also formulating a theory of phase transition as a whole, and superconductivity was one of their goals. They wrote down a phenomenological theory called Ginzburg-Landau theory of phase transition close to critical point, and they were able to get many things out of that theory, which were experimentally verified in superconductors, but they did not have a microscopic understanding of the origin of this attractive interaction, how two electrons or a large number of electrons belonging to a Fermi sea interact via this attractive interaction to form a ground state that is superconducting. So, later on of course, these two theories were connected from microscopic theory. People were able to derive the connection to Ginzburg-Landau theory. So, that is an aside. Ginzburg-Landau theory will come back to us again when we discuss electrodynamics of superconductor and the vortex lattice, for example, in type 2 superconductor. But for the time being, let us discuss the microscopic theory, which came to be known as BCS theory. As a prelude to that, there was a famous calculation which is done by Leon Cooper, and you can see that Leon Cooper is part of the team of three who discovered this microscopic theory of superconductivity. And Leon Cooper solved a problem which is, as I said before, just take a Fermi sea, put two electrons above the Fermi level, so they are pretty close to Fermi level, but just above, because up to Fermi level everything is free, occupied already, nothing is free, no states are free. So, then these two electrons interact via a retarded attractive interaction, and that I discussed the origin of retarded interaction, and then under these conditions that these two electrons are interacting via this attractive interaction, Cooper was able to show that there is a bound state that forms whose energy is negative with respect to the Fermi level. So, that means these two pairs form and their energy is gained, because their total energy was, for example, twice the Fermi level, because both of them are pretty close to Fermi level, but their new energy under this attractive interaction was less than this 2 EF, and that means that there is a gain in energy by exchange of phonons. So, this this interaction, as I discussed,
is via exchange of phonons like this, and so it stabilizes these two electrons, and then the natural conclusion from there on would be that what happens to the Fermi surface, because now if every electron finds a partner and pairs up and lowers its energy, then this will be a cascading effect, and almost all electrons below the Fermi surface will try to go above the Fermi surface, and then so those which are very close to the Fermi level, for example, they will first go to the top by slightest excitation to above Fermi level, and then use this attractive interaction to form a state which is lower energy. And so this will go on, this will be just like a cascade, domino effect. Almost all the electrons will start doing this, and that means the Fermi surface becomes unstable. So this is what the consequence is, and this would be the many body consequence of such a calculation, which such a proof that Leon Cooper had come up with. But of course, there is a caveat that there is all these electrons are also interacting with these pairs. So the question is how to tackle this many body problem. So it is not a one step from that Leon Cooper's calculation, which I will outline now. It took a while to go from Cooper's result to the BCS theory. So this I had discussed, how this attractive interaction retarded in time, separated in time, works between two electrons, and how screening helps in reducing the repulsive interaction within a short distance, so that this attractive interaction is dominant over the length scale and time scale that we are talking about. Okay. So let us now start discussing the Cooper problem, which is what we were discussing, and as we said that the two electrons of momentum k1 and k2 both just at above the Fermi surface, they interact via this attractive interaction, and k1 plus k2 equal to the scattered states k1 plus k2 prime, k1 prime plus k2 prime, the momentum of the scattered state equal to k. So, see, any interaction in quantum mechanics can be thought of as a scattering process. So, this is this process. You start from k1 and k2, and you will end up with k1 prime and k2 prime, but you can conserve the momentum. Okay. So this is what we are going to show how on a Fermi surface how does it look like. So these are the two Fermi spheres we plotted, and these are the annuli over which in the range h cross omega d by. So this delta k is over which the interaction works, and the energy range will be h cross omega d by across the Fermi surface. So this is delta k. Sorry about this problem. Okay. So and then there was this k1 and k2, these are the two momenta k1 and k2. So one can draw a minus k2 from starting from this center, and so this will be the k1 plus k2, which is k, which is this one. And we argued that the gain in energy through this exchange of phonon has to happen in this region where K1 and K2, K1 and K2 some coincide. So, K1 minus, so these are the region where the two K1 K2 spheres, this is a circle, but this is in 3 dimensions, is a sphere. So, these two circles of K1 and K2 they coincide at these regions of phase space, in these regions of the the state space, and then of course, this is to be maximized to get the maximum interaction between them, so that they gain the maximum scattering. There are maximum number of scatterings that reduce the energy, as I said. So, so energy reducing exchange processes are maximized if the joint area, the shaded area can be increased. As the shaded area increases, there will be more and more scattering, and so therefore, the energy will be gained. So, this is the whole idea. Okay. So, and of course, this is your Kf. And when is this shaded area maximum? Well, it is maximum when k is equal to 0. So, k equal to 0 is the maximum. So, K1 equal to minus K2. That means, these two spheres or two circles here in this drawing, where I have to draw 2 dimensionally, but these are spheres and these two basically coincide. So, then that means this relation has to be satisfied for maximum gain in energy. So, maximum scattering possible maximum area for scattering, okay, in this phase space. Now, that means that of course, there are other regions also, there are other k values where the scattering will also happen, but what Leon Cooper decided is that we will look at only the maximum scattering regions where the area is the maximum, the area of intersection is the maximum. So, that is where he wanted to concentrate, and because the amplitude is highest there. Of course, the rest will also add, but this is what one can one considers, and that is because then life becomes simpler also, because K1 equal to minus K2. There is only one momentum you have to take care in your theory, which is K1, for example. Okay. So, the joint two particle function in this case consists of very simple choice. This is normalized in a box 1 by L cube e to the power I k dot r, and into 1 by L cube e to the power minus I k 1 dot r and it plus I k 2 dot r. Okay. So, which is equal to 1 by L cube e to the power I k r 1. So, this is r 1 and this is r 2. So, I k dot r 1 minus r 2 for 2 electrons at r 1 and r 2. So, this is the joint wave function that one can write, a 2 particle wave function. Okay. So, let us now use this wave function and calculate the simplest possible case, where we will write down the Schrodinger equation for the two under the potential and try to see if there is a bound state. Now, of course, this wave function is too simplistic. One can have all possible combinations of such states, that will be the most general representation. So, that is what says most general representation of a 2 particle state for the case of a non vanishing interaction is given by the series. So, one can write down psi of r equal to 1 by L cube sum over k some g k weight factor e to the power I k dot r, where r is equal to r 1 minus r 2. Okay. So, the summation of this is confined to this k equal to k 1 equal to minus k 2. So, that is already there. Now, that restriction means also in terms of energy, that you are confining yourself within within an annulus, just as I drew in the other case in the momentum space. So, this is also in the momentum space, but the corresponding energies should be within E f plus h cross omega d and E f minus h cross omega d in that range. So, that is what as I mentioned, the interaction is retarded. Retarded means it is separated in time, which means it acts only on a narrow region in the energy space. And how much what is that energy space? Well, it has to be connected to the phonon energies, and that is exactly that is the lowest, that is the low energy scale here for because the Fermi level is of course a very large scale, compared to that h cross omega d y is much smaller, and that is because phonon is responsible for causing this interaction, attractive interaction, it is natural, it can actually be shown easily that it is attractive over a region which is in energy space, it is about h cross omega d y. Okay. And Gk is the probability of Gk square, of course, is the probability of finding one electron in state k and other electron in state minus k. Okay. So, then of course, you also know that Gk, this k has to be restricted in this region it is 0, and in this region again it is 0, because it is within that small region. Now, just use the Schrodinger equation, which is what is written here. So, it is minus h cross square by, so it is we are doing a 2 particle problem, h cross square by twice m delta 1 square plus delta 2 square psi r 1 minus r 2, or I can write as they write. You can also write I mean it is of course a function of r 1 minus r 2 as we have seen. So, you can also write it as r 1 comma r 2, which is the way it is written here, but anyway. So, let me just put that r 1 minus r 1 comma r 2 plus this interaction v of r 1 r 2 psi r 1 r 2 equal to some E psi r 1 r 2, which let us take as epsilon plus 2 E f naught psi r 1 r 2. Why does one do that? Okay, so let us see why one does this. The reason is that suppose the 2 electrons were exactly at the Fermi level, then the total energy would be E2 f 0, and now we have taken them slightly above the Fermi level. So, that means there is an energy, very small amount of energy epsilon. Now, at the end of the day, if it turns out that this epsilon is becoming negative, that means there is a solution which actually stabilizes it, this kind of a 2 particle state. So, these two particles form a bound state, and that is why one is taking this, and the end game is to show that this epsilon has a negative value, and that is what we will do, and that is what Leon Cooper also did. He showed that under certain conditions, the conditions I will outline again, this epsilon is indeed possible to be negative. Okay. So, let us now do one thing, that we multiply this equation, which is this equation by So, let us just write down, for example, first this g k e to the power I k r in this equation. So, this will be minus h cross square by twice m sum over k delta 1 square plus delta 2 square will operate on e to the power I k dot r. So, it will give you 2 times h cross 2 times k square here times g k, okay. And then of course, this e to the power I k dot r 1 by L cube and all that, okay. Then there is this v term. So, that v term is here, this v term v r 1 r 2. So, let us just put it in v r 1 r 2 sum over k g k e to the power I k r 1 minus r 2 and of course, the k sums are always restricted within that window, but okay. So, that is there, and there is 1 by L cube. So, that is the v term giving, and the e term gives me e times sum over k g k e to the power I k r 1 minus r 2. So, these are the two terms in addition to the other one that I have. Okay. Now, what one does is that one uses a trick so that you can get rid of this sum over k, and so that is what is written here. You multiply both sides by e to the power minus I k prime dot r and then integrate over all r. Okay. So, let me show you what happens to one of these terms. For example, this one had g k e to the power I. So, this had minus h cross square. So, this becomes plus, because this is there is a minus that comes in, sorry, there is a minus 2 k square, because e to the power I k del square of I k will give you e to the power I k dot r del square operator will give you minus k square, twice that will give you minus 2 k square. So, the result is h cross square k square by m sum over k g k e to the power I k minus k prime dot r integral over r. Okay. So, that is what you will get from the first term, for example. Now, this integral gives me a delta function, and that delta function just reduces one of these integral, this whole thing becomes just 1 k, the k summation vanishes. So, that is this term h cross square k square by m of g of k. So, this is k equal to k prime. So, I can replace it, write as k prime here, but since k, I mean I can choose that k prime as my k. So, it does not really matter, this equation, instead of writing for k prime I can write the equation for k. So, that is what I am doing, but the summation vanishes, because k is now fixed to k prime and that k prime I am calling as k here, plus 1 by L cube g of k prime v k prime sum over k prime equal to epsilon plus 2 E f naught G of k. Okay. So, this V k k prime is basically just there, the remember that integral that we had. Okay, so let me just show it here. Yeah, this is the one where we put this sum over k, this one. So, then this is multiplied by V r 1 r 2, and then I multiply again by e to the power minus I k prime r 1 minus r 2, and then sum over integral over r. So, that whole thing is now called G of, just put it in and you will see that this is what G of V of k k prime is. V of k k prime is just this integral V of r is r 1 minus r 2 e to the power I k minus k prime so, let me just check the signs, I k r 1 minus r 2. So, I have plus I k minus k prime dot r d 3 of r. So, this is my V of k k prime. So, this is r independent, r is integrated over, it only depends on k and k prime. Okay. So, this V k k prime basically describes scattering of the electron pair from k minus k. So, from k minus k state to k prime minus k prime. So, this scattering is described by the potential. Okay. Okay, fine. So, now comes this approximation. Of course, this is a complicated equation, there is a sum over k prime here. So, you cannot solve it so easily. So, this is my equation. This I have to solve, and then there is a k prime sum. So, each k is connected to all other k, each k prime is connected to all other k's. So, I can't solve it analytically here. Okay. So, what one does is that one now motivates physically. So, that physical motivation is already there, we already know that the V k k prime is negative for a region where V 0 is positive, for where this k and k prime are such that E f 0 and E f plus h cross omega dy within this window, the corresponding energies h cross square k square by twice m and h cross square k prime square by twice m are within that region. So, these two energies of the two electrons are just above the Fermi level, but within the range of h cross omega dy. So, just above Fermi level E f 0 in a region which is just omega dy above h cross omega dy above it. So, both the energies of these original electron, the electrons that are participating, that are scattering are here. Okay. So, with this scattering is basically the two electrons at k minus k going to k prime minus k prime. So, and in all these, for all these k and k primes, the energies must be within this region, and that is what this condition here tells you. Okay. Okay. So, if you do that, then of course, your life becomes much simpler, because now V k k prime is no longer dependent on k k prime. So, immediately a huge simplification occurs. What you get is minus h cross square k square by m plus epsilon plus 2 E f 0 is into G of k is equal to V 0 by L cube sum over k prime G k prime. Okay. So, this really is an enormous simplification, because look at this right hand side, this object here is now k independent, because all k's are summed here. Okay. So, this is just a constant, I can just write it as sum minus lambda. Okay. It is just a number. Okay. This is just a k independent object, just a number sitting here. On the left hand side, of course, I still have g of k. So, the lambda is equal, lambda is this entire object, this entire object is called lambda. Okay. See, there is a minus V 0. So, I have to be careful. So, this was G k k prime. Let me just see how it, whether there is a minus and V k k prime. Okay. So, this is h cross square k square by m, this thing equal to V k k prime, that is correct. Okay. So, this was, there was a minus sign here. Okay. So, my remember h cross square k square by m has been brought to the right, and so this is okay. So, that is perfectly all right. So, in this under this condition, this whole thing, the left hand side is just now a lambda. So, let us just go one more step, that is independent of k. Now, what one can do is that one just writes g of k equal to okay. So, let me just check this is once more how they defined it. Okay. Okay, fine. G of k is then what I do is that I multiply it by V 0 by lambda cube and sum over k, and this is equal to lambda by sum over k lambda by h cross square k square by m plus epsilon plus 2 E f 0. Okay. So, all I have done is that I have first written g k equal to minus lambda divided by this thing, and then I summed over this both sides by multiplying by V 0 by lambda L cube. Okay. Now, you can see that this thing is again minus lambda. So, this is becoming lambda minus lambda, and that cancels with this minus lambda here, and so this left hand side is minus lambda something, the right hand side is V 0 by L cube sum over all this 1 by h minus h cross square k square by m plus z plus this epsilon plus 2 E f 0, and then there was this minus lambda. So, these two cancel, I get the equation that is written here. So, that is that is this equation, okay. And this is the equation we have to solve. Okay. Now, this we redefine just a definition, one uses a definition as C equal to h cross square k square by m minus E f 0 okay. So, that is one is defining with a 2 here. Okay. Okay.
So, that 2 is so this is like a single particle energy minus the Fermi level. So, original electronic energy measured from the Fermi level. So, that is what this is. So, you define this and then your equation becomes then you use the standard standard relations that sum over k can be converted to an integral over k because there is a large number of k's as we did in the free electron theories. And then of course, there is this other relation that we used that any integral like this of a function which is a function of epsilon k only can be converted to a density of states integral over energy. This is an integral over k, whereas this integral is over energy. So, this is doable. So, with this we will now start solving this Cooper problem and see what happens.